In the previous class, we looked at disks and some aspects of scheduling. So, we will spend a bit more time looking at some other details corresponding to disks. Particularly, we have to look at a protocol called the Scsi protocol or the Scsi based devices, and this is the first major disk interface that became popular. Previously, all disk interfaces were proprietary, and once this particular interface became popular, the disk industry really took off quite a bit. One of the most important things about the Scsi devices is that it allows the computer software that manages disk to be independent of the various types of peripheral devices. So, basically what is happening is that the software basically sends certain commands, and it is the business of the device itself to somehow execute those commands, and these commands are standardized. That means that any number of guys can be disk vendors, but they all have to satisfy this protocol. Of course, each vendor can provide some additional functionality, but they are considered optional facilities which are not to be assumed to be present in other devices, other disk devices. So, in a sense, it allows people to have a common set of protocol, let us say transfers that you can assume across all the disks, and certain additional things which can be, let us say, optional. Another thing that is important about Scsi is that it is based on a client server architecture, and this actually helps it to keep this particular protocol survive for a for longer periods of time. I will mention what this is soon. In this client server architecture, there are clients called initiators who issue requests, and there are, sorry, there is a mistake here, there are servers called targets that respond to initiator requests. So, basically the way we understand this devices now is that there are parties called initiators that issue some requests to read something, for example, and servers are those which actually respond to them. Since it is a client server architecture, it turns out that sometimes you need something slightly different from a client server architecture. A good example is, suppose I am doing a backup between tape and disk. Now, these are already two entities, but I want to have control, I want to control this transfers through some other entity. It could be some piece of software. So, now there are three parties involved. Now, in a client server architecture, typically you usually only have two entities, client and server. So, this kind of things may not be appropriate in some contexts. So, you have to work around this client server architecture in case you need to do things like backup. And notice that backup is an important aspect of storage systems. So, I think it is nice that they came with a client server architecture, but sometimes this may not be exactly what is required. Now, Scsi commands are sent in units called command descriptor blocks. So, these are the software which is managing these particular devices has to send all the commands in these command descriptor blocks. There is also some, if you want to make Scsi adaptable, not only that is useful in the context of a single desktop system, but also useful across longer distances, you need also a transport layer, and it turns out that there have been quite a few varieties of transport layer protocols that have been devised. One good one is iSCSI. It means you can transport the Scsi commands on internet. iSCSI is basically Scsi over internet. Okay. There are also other protocols like FCP, this is a fiber channel protocol, and these transport layer protocols, they govern the flow of Scsi commands and data blocks. Okay. This iSCSI, for example, goes over TCP/IP, the internet, but FCP will go over typically over what is called a fiber channel protocol. Nowadays, even these you can also use internet to transport this some of these proprietary fiber channel related protocol units. If you look at the Scsi system, the early Scsi assumes a bus-based architecture. Again, going back to our previous classes, you notice that network became really, let us say, fast only post 1980s. So again, Scsi also came around at the same time, 1980s, but Ethernet was not very common those days. So they never seriously thought about coming up with some network-based architecture, and they assumed electrically based, let us say, system, and essentially a bus-based system. About, for example, you will have a bus on which you can put about 7 Scsi devices. Okay. So that's the kind of stuff they came up with. And one thing about this kind of bus-based architecture is that if something goes wrong, you try to retry, and the retry timeouts are usually quite long. So and basically, if there are any bugs in the system, they have to be recovered from, and it can take some time. Okay. Now, if you are thinking about a bus-based architecture, for example, they are not really efficient in recovering from packet loss, because you need to actually, if you are not going for a bus-based architecture and you want to go for a network-based architecture, you can't have the same type of timeouts that are there in the case of a bus-based architecture. Okay. So you need to have slightly different kinds of models, and all the same, it turns out that drivers that were written for older Scsi standards, they have been modified so that it can work for network also. Okay. And typically also early Scsi would not try to do a lot of parallelism, because it was slightly difficult to, in those days it was, there were not too many disks around to be put on a single bus. So usually the amount of storage that was being talked about was quite small. So there was hardly any serious attention paid to parallelism in the system. The later versions of Scsi, for example, Scsi 2 and Scsi 3, they systematically look into this more seriously. We will look at this soon. Other thing that one has to think about Scsi is that usually you can ask it to, if transfer is made, and only when the status OK is sent, the device has to commit the data, and it cannot lose data after that. If it loses data after that, then it's considered a malfunctioning device. Okay. So essentially what it means is that the devices can do some caching. For example, I can have an electrical transfer from one buffer to another buffer. The buffer from the let us say sending side, it can go to the buffer on the storage device. It can stay in the memory for some time, but once the status is sent, that means it has to be committed to the persistent part of the storage system. Okay. For example, if it's magnetic device, it has to be copied onto the magnetic portion of the system. It can't be sitting in volatile memory. It has to be in the persistent part of the memory. Okay. Now, if you think about if you think of interconnections, then you should look at the kinds of response you expect from the interconnect, because it turns out that for disks usually you have a few milliseconds for access, and if you are using caches, it will be sub-millisecond. So the interconnect latency that you are using to connect these two, for example, the initiator and the target, for example, should be less than, typically much less than the storage response time, for example, a few milliseconds for disk, etc. Let us look at some of the terms. I should mention that most of this was devised, the standards were devised in industry. So some of the terms are, let us say, not exactly obvious what they mean. So we'll just go through it a bit. What is the target? target is as I mentioned, there are two parts to the Scsi client server architecture. The client is basically the initiator. Okay, it creates and sends Scsi commands to the target, and the server is basically the target. Now, the server also can be thought of as a collection of functionalities, and so these are, each functionality is considered as logical unit, and they can be directly addressable on the network or on the bus. Okay. What it means is that I can have a storage device, it can export multiple functionalities, and each of them can be independently accessed. A good example of this could be in a tape device. Oftentimes, the rewind function is taken to be a logical unit. Okay. So, if you want to make the device rewind, you just say you send it to that logical unit. A task is basically a linked set of Scsi commands, and basically, because if you look at storage devices, they oftentimes they have to seek to a particular place. So, I might want to have a set of commands which basically say seek there and read from there. So, this is an example of a linked set of commands, seek to that point and then execute read from there or write to that point. This is an example. There are other aspects. For example, each task can also have some attributes. We will go into some detail about this later, and it can be tagged or untagged. That means that each IO process, right, basically each activity that you are asking the target to do can be tagged, so that you can essentially refer to it again later, or it can be untagged, means it has to be executed in the same order it came in. It can be simple, ordered, head of queue, etc. I will come to this later. Okay. One important thing about Scsi is that only one command in a task can be outstanding at any given time. Okay. And the tags, as I mentioned, is used by target to distinguish between different tasks. What it can mean is that same disk can be accessed, can be servicing multiple initiators. So, I might want to distinguish between each of those initiators, and the initiator themselves, each initiator can actually send multiple commands. So, within each initiator target, I might have multiple commands, and I want to be able to distinguish between them. I think the way to think about it is similar to in the case of Internet Protocol IP. You will notice that there is something called the machine comma port. Okay. So, the internet connection is given by machine 1 comma port 1 followed by machine 2 comma port 2, that is the connection. Similar here also, the connection is basically that of a initiator comma tag 1 with a target and its tag. Okay. Basically, I want to be able to, just like the port numbers are used in the case of internet to distinguish between various services, I also need to be able to use way to distinguish between various IO processes that are being initiated at the target. So, the tag is basically used for that reason. Again, the Scsi devices, as I mentioned, they try to make access to the devices independent with respect to the particular device. So, the software does not have to know much about each the specifics of each device. So, just like you have the notion of virtual memory, and you do not have to know the details about the memory subsystem, here also you have the notion of logical bus address. Okay. And what is, I am sorry, I made a mistake, this is logical block number. I do not know why I have made this logical block address, sorry, I made a mistake here. Okay. So, this basically is some kind of a virtual address, and it is the business of the device to map it to whatever physical entities that are there in the system for that particular piece of information. Okay. So, logical block address is basically somewhat abstract notion about the way the user actually refers to some piece of information, and it can be it needs some kind of translation by the device before it can be accessed. Again, this is again so that the software is independent of the particularities of the device. Okay. Similarly, the logical unit number, I mentioned that a target is collection of logical units, and each functionality is given a number. Okay. Typical thing is that I can have let us say multiple partitions, each partition can be given a logical unit number, or I can have certain functionalities like rewind functionality as a logical unit number. We will just quickly go through how the Scsi functions. Again, all the terminology as you can see is based on the notion of an electrical bus, but I think historically that is how it is referred to. Okay. Bus free means there is currently on the bus there are no active requests, so it is completely free. If there are multiple accesses at the same time, you need to arbitrate. Again, there is an arbiter which does it, and then the initiator selects a particular target, and then after selection the target is in control. It is a very interesting model where the initiator, once you have selected the target, then the target is completely in control after that. And the reason why this is done is because we discussed it earlier. It is because the targets are extremely slow. Because the initiator could be a piece of software running on a very fast machine, and it could be running at speeds of nanoseconds or tens of nanoseconds. The target on the other hand is a very slow device. So, when actually it finally gets to seek to the particular point can take large amount of time. So, the thing is this, I do not want to keep on polling all these things, even polling is an expensive affair. Okay. So, the target is in control, and then that it is basically the thing which decides how to communicate with the initiator after that. Okay. It is like the way interrupts are used. Okay. So, target decides when to receive message, command, data from the initiator, okay, or send data. So, every single thing, whether when to get the message, when to get the command from the initiator, when to get the data from the initiator, or after the operation is done, when to send the status initiator, all of it is initiated by the target. Okay. Okay. So, for example, start with bus free, arbitration, selection, and then once the target is selected, the command is sent, okay, and the target is now in control. It will say that I am ready to accept your command, and I am ready to, I have allocated buffers so that when you send information I can pick it up. Now, again there is a big difference here, because you notice that the target is a slow device and does not have too much memory. Okay. So, it has to completely control when it is ready to access things. Otherwise, the fast CPU or fast devices, fast memory, whatever, can essentially overrun the buffers on the target side. So, that is the reason why the target is in complete control. It decides when the initiator can send something. Okay. So, every single thing has to be initiated by the target after this phase, of the selection phase. Again, what is reselection? Once the target has finally seek to the particular place where the data is, then it again reselects, and then afterward it tells the initiator, I am ready now, I have allocated this amount of buffer, and now you can send me this amount of data. Okay. And sometimes it turns out the initiator has to send some critical information to the target. Again, the way it is done here is just like there is an interesting model here. Again, the initiator essentially sort of gives an interrupt to the, something like an interrupt, it is called attention. Okay. It gives attention signal to the target, and the target now says, I got your attention signal, please send the message you want to send me. Again this target is in control. It actually tells the initiator, I noticed that you wanted to make me respond to something, I am now ready, please send a message, etc. Okay. Same thing with status also. If it turns out that a particular operation is done, then the to send the status information to the initiator, right, even that basically the target basically it sends a message saying that I am now ready to send a message, then you tell me what kind of stuff you want, then I will send it to you. Okay. So, this is an interesting model. I think the high level thing I want you to remember about this particular thing is that once the target is selected, the target is in complete control because it is the slowest device, it has to figure out what to do. It cannot be overrun, it has only a finite amount of memory, and therefore it actually controls everything. Okay. And basically because it turns out, again if you think carefully a bit, there is a read and write operation. Read operation is going to be on the device, so you don't need to do any flow control on that. Okay. Basically because the stuff is coming from the device, the slow device, so there's no need to be done, there's no need for it to do any flow control on reads, but writes are coming from the fast memory or whatever, right? Flow control has to be done because some kind of asymmetric aspect is there. Okay. Okay, just let's look at the protocol itself. This initiator is a target. Now I want to do a write. So the initiator can have a tag for it, saying that this is a particular type of I/O process that is going on, some kind of just like as I mentioned earlier, in the case of internet you have the notion of machine comma port number, right? That identifies a connection. Okay. So this is on the one part of the machine comma port number in the internet kind of case. That's one part of it here. This is basically the logical block address, and this is the length. Now once this is given to the target looks at it, says that this guy wants this amount of memory to be, data to be written. So it looks at it and says, okay, it has to allocate the buffer on the target side. Once it has done it, then it says ready to transfer. Again it says with respect to the same, it sends the same tag back, and then it says that on my side I have a tag also. Just like the case of internet protocol, you have port 1 on both sides, right? There is a port on the sending side and the port on the receiving side, same thing here also. Okay. And then after that you can do a write, and then once it is done you can send a status back. Okay. This is a simple example of a write. Similar thing with read. As I mentioned to you, here there has to be flow control. That's why the ready to transfer is there. Okay. Here there is no need for flow control. That's why you will see that you just say read command, and then the data is sent out like this, and then the status also is sent out. Okay. I hope this part of it is clear. Why there are 4 parts to it and there are 3 parts to it. It's basically because there is no need for a flow control on this part. Okay. So, it's a simple model of Scsi execution. Now we can try to make it slightly more interesting. Now let's say that instead of an initiator talking to a target directly, we also have a controller in between. Okay. And this may be needed for many reasons. Reason could be that the target is sending too many interrupts to the initiator. For example, your CPU, okay, and the CPU doesn't want to be bothered by the interrupts that the target is sending out. The reason could be that initiator wants a write of, let us say, 64 megabytes, and the target can only accept, let us say, every some smaller amount, let us say 4 kilobytes or 16 kilobytes, something like that. That means that for every 16 kilobyte, that guy has to keep on interrupting the initiator. So you don't want that to happen. So you want to put some agent, a controller, often called a host bus adapter. Okay, that's what is guys. Now how does this particular thing work? Actually it turns out that all these guys have to speak the Scsi protocol, all of them. Okay. So how does it work? Just same as before, write command, initiate task tag, LBA length, and the controller can respond to the initiator because these 2 guys are speaking Scsi now. Okay. So because the write, again the controller should not be overrun, therefore the controller will basically say, okay, I have allocated some space on my host bus adapter card, there is some amount of memory there, and I am willing to accept a particular length. Okay. So and then finally it says write, and then it is returned to the controller. Typically these transfers are electronic transfers, okay, because on this side there is some memory, on this side there is some kind of electronic memory. Okay. Now once this particular initiator has returned to this controller, now the controller in turn will again use Scsi protocol to write to the target. Now here, if the controller has enough memory to write to this, right, it can do it in one shot. Typically the target might not have access to memory. For example, I remember once upon a time in the 1980s, this target might have only as little as 64 kilobytes of memory in the target, and initiator might want to do a write of, let us say, 1 megabyte, and typically what would happen is the controller would have something like 128 kilobytes or 256 kilobytes of memory. That means that initiator would write in chunks of 256 kilobyte, and this itself again is going to be split up and written in terms of 64 kilobytes to this guy. Okay. So that means that this write command, you have a initiator task for the controller. Okay. This again a tag for the controller itself, and then there is a LBA that the controller has to come up with, because I am going to use, this is going to be a long one, let us say some 4 megabytes. So then this party has to say that it is at 256 kilobytes, then 512 kilobytes, then 1 megabyte, then 1.5 megabytes, etc. That is what this is. It is basically saying at this offset please do it, and for this length. Okay. Again, these two talk to protocol, these two guys talk the Scsi protocol again. So this target will now tell I am ready to accept your write, let us say data, and I have allocated my buffers, therefore please go ahead. That is what this is, this particular message is about. Okay. So this length that this target accepts is basically what its memory can handle. Okay. And then this is written, and you repeat this as many times as necessary till the whole transfer is done, and then this party says that I am done, and this actually is taken by the controller sent back, right. Now this is perfectly fine as long as in a single desktop system. In a single desktop system, your electrical interfaces are quite fast. For example, in desktop systems, you have once upon a time started with 5 megabyte per second, then it became 10, then it became 20, then it became 40, 80, 320 megabytes and 640 megabytes per second. So these things are quite fast, these electrical interfaces. 640 megabyte per second is equivalent to about 5 gigabit per second. Okay. So these things can be quite fast. Okay. But suppose I am doing the same kind of idea, but on internet. If I am doing internet, it turns out that sending it back and forth between 2-3 parties, initiator, controller and target, can be a bit, let us say, wasteful. So you might want to do something better. Okay. So here already we have taken care of segmentation, assembly and reassembly here. That is what we have done here. But we would like to also do something more efficient. Okay. How is this to be done? There is a way to do this also. What we can do is, you can have essentially equivalent of 3-way transfers, this initiator, controller and target, and the target, initially the initiator also sends similar type of information, except that there is an additional piece of information about a connection ID that is kept, and the idea basically is that the target should directly send the information to the initiator. Okay. And it is repeated these 3 steps as necessary. Okay. The idea is basically, instead of, if you look at the previous one, right, you had to transfer it from here to here, and then finally that's your transfer from here to here and from here to here. Okay. So you want to avoid this expense. So if it is possible, you might want to do it directly between initiator and target. Of course, the number of interrupts etc. will be high in this case, but if you are talking about at the level of internet speeds, probably the number of interrupts that are coming in are manageable. It is not a serious problem, because the rate at which you are sending stuff is not very high. Okay. So this is one example of a 3-way transfers that can be done. The interesting thing about this is that each of these parties are essentially speaking Scsi protocol. Okay. Because it's like both are, the Scsi protocol is client server, it is feasible for us to keep introducing intermediate agents. Okay. And that's the reason why the Scsi protocol, since 1980s, it is still going strong. Okay. Whatever new technologies are coming in, whether it is storage array networks or there is any other type of networks that are coming in, they can essentially modify things here and there a bit, and the same Scsi protocol can be still used. Okay. Again, for reads also you can do the same things. Again, what I showed you earlier was for writes. Okay. Basically, it is coming from initiator down to the target, and this required some kind of flow control, whereas in the case of the 3-way transfers, it's slightly simpler. I can directly send it as fast as I can. Okay. And again, something similar, except that sometimes there could be some interesting issues with respect to some of this message is coming out of order. Okay, so this is something to be taken into account. Again, you'll notice that whatever we're talking about right now is actually similar things you have to worry about, whether you're doing it at this low level, at Scsi level, even if you do it at slightly higher levels. For example, if there are two file systems talking to each other, they may also have to do some of these things. Flow control, they may also have to worry about how to segment things, how to reassemble things. Okay, all those issues, whatever we're talking at this level, are also applicable even if you try to go at higher levels. Okay, almost every single issue. Okay. Here, for example, one of the things that this particular Scsi protocol doesn't worry about is security. So there is no question of any encryption, etc. here. And Scsi has not been defined using security in mind, but iSCSI has been defined assuming security in mind. Okay, so it uses the Internet IPsec protocol if any security aspects have to be handled. Again, to think about this Scsi architecture a bit more in the traditional style with respect to how networks are described, you'll see that there is an application layer, there is a transport layer, there is an interconnect layer. This is closer to your data link layer. This is closer to your TCP slash, I shouldn't say it's TCP level, it's basically the actual protocol services here. Okay, and this is the application layer. For example, if it's a tape or a CD-ROM or a DVD, okay, it has specific commands. Okay, those things are handled here. Okay, so the thing to do is that this is basically the thing which allows you the interconnections. This is the thing which is connected with just the layer above the transport layer. You have some presentation or the protocol aspects of it. That's what is being handled at this point, and this is where the application. Okay, and you'll see that iSCSI and some other fiber channel kind of protocols operate at this level, whereas the TCP/IP and the physical layer of fiber channel or InfiniBand, all these things operate at this level. Okay. If you look at from the Linux point of view, you will notice that the upper layer, as I mentioned in the previous class, you have three levels: upper layer, middle level, and lower level. So, for example, disks have a particular type of software, you might call application level software for handling disks. There is some specific type of disk for handling CD-ROMs. This is one for tapes, and this is for a generic device, okay, without any structure like disks or CD-ROM or tapes. Okay, and basically here is the mid level where all the commands are converted to Scsi requests. This is where basically I mentioned to you about the Scsi requests, about whether it's some ready to transfer, etc. Those kind of commands. Those things are done here. Okay, and this also manages the interaction with the host bus adapters. If you are thinking in terms of interconnect, for low level it's basically through HBA. If it is for if you're using internet, for example, it will be iSCSI followed by TCP/IP. Okay, this is what basically this is basically interconnect part of it. Okay. So again, the important thing to remember is that you try to ensure as much as possible to reuse code if you can, and the way to reuse the code is basically to take out the interconnect part, which is quite different for local disk versus internet, and then all disks, for example, have this particular piece of software, and CD-ROMs, DVDs, etc. will use a slightly different application layer, you might call it. And because there are some subtle differences with each of these things, you have to handle it specifically. Okay. So again, there are lots of issues here also. For example, parallelism. Suppose this is a Scsi layer in Linux, right? So upper layer is handling this. How many, if there are multiple disks, can I pump all the disks at the same time? Okay. Again, this particular device, this particular software has to take into account how many kernel threads are there which are actually pumping requests into this part of the layer, whether this itself is let us say parallelized. Okay, there will be a lot of locking and other kinds of considerations. All kinds of issues will be here. Okay, so each of this looks, I mean, say if you think a bit more carefully. There are a lot of issues that need to be handled before you have a working system. Okay, just basically we will continue a bit more on looking at Scsi, because the reason I am doing so much, taking so much time in talking about Scsi is that everything that we talk about Scsi here, you will find that this is similar things have to be done at even higher levels. Okay, the same issues keep cropping up again and again. Okay, so let's just look at Scsi 1. Scsi 1 was one of the earliest Scsi standards, and they already had provided something called linked commands. As I mentioned earlier, if you are talking to a tape, you may want to seek to a place and then read something, right? So that's why you would like, instead of sending two separate commands, you would like to send a seek plus read. The reason why this is important is because for atomicity reasons. For example, the tape can be used by multiple initiators. One guy seeks, and then before the read command has made its way, some other person also seeks somewhere else. Okay, right? There can be some problems. That's why you need to ensure that link commands are present. Okay, so then there is also something called IO process keying. Basically, an IO process is basically one unit of work that you want the target to do. Okay, so there could be a queue in the target, and each IO process can be given one entry in it. Okay, so the commands are executed in sequence. Okay, suppose we look at the queuing in the IOP. Okay, this was provided in Scsi 2. So there are varieties of models. There is untagged model and the tagged model. In untagged model, it allows the target to accept one IO process from each initiator for each logical unit or target routine. Okay, so target can accept commands from an initiator while executing IO process from another. Okay, so the idea is to allow some kind of parallelism, and it is not as much as this one. For example, in the tag case, it can accept a series IOs from the same or different initiators. That means I have there is initiator 1 and initiator 2. Initiator 1 can send 5 or 6 requests. Initiator 2 can send 3 or 4 requests or whatever number. And the requests sent by initiator 1 or initiator 2, they can be again use elevator algorithm like what you saw before, this scheduling, that can also be done. So in a sense, what I can do is with tagged, I can, because I have information about each of the requests and I know which which initiator is doing it, I can actually execute them in the order that's best for the device, and they can respond to it, to the actual initiators who initiated it without any difficulty. If I don't have tagged ones, I'm not really in a position to do it. Okay, so basically the tag queuing allows drive to accept multiple commands from each initiator. So I think basically once you have notion of tagging, it turns out you need to start thinking about how do you order things, can you mix tagged and untagged things, what are the error models. Okay, again, if we think a bit about some of the issues are similar to what has to be done in the case of a multi-threaded system, right? What is ordering between requests if I am accessing memory, okay, and can I have certain consistency models, right? For example, is it possible for me to say that this particular memory operation has to be committed before I look at any other memory operation? Similar things. For example, is an error. If there are multiple operations that I am doing in a memory-based system, how do I report errors? Okay, so even Scsi also has to look into similar issues. Okay, so we briefly look at this. So if you look at simple, there is something called simple queue tag. Okay, so all it's saying is that an initiator sends a new request, and it is just added to the command queue, and the target can actually reorder it. It's up to it. Basically, if it's a simple queue tag, it means that the target is completely free to reorder it the way it wants. Okay, nobody is stopping. Whereas there is something called head of queue tag. What this means is that there is something very critical that has to be done. Okay. There is an absolutely critical thing that has to be done for the sanity of the system. I send head of queue tag, that means it is going to be executed immediately after the current one is finished. Okay. Okay. So, an ordered queue tag, it is the same except that in order of entry, okay, except it is not true for the head of queue tags. Okay. And if you look at the Scsi manuals, you will find a lot of details about this, and because storage is a critical part of the infrastructure, so if you get something's wrong, you are going to lose data. So that's why there's a lot of effort in specifying exactly what has happened here. Okay, I'll just read out one or two things just to get an idea. Okay, if you get a command with a simple queue tag, okay, prior to a command with an ordered queue tag, okay, then you have to execute that command before you get the ordered queue tag. It is something similar to if you are looked at memory subsystems, you have the notion of what's called a barrier, right? So, if you get a barrier, you have to execute all of those things before, then only you have to do commands after the barrier. Okay. Now, the ordered queue tag message basically is some kind of a barrier. Okay. In a sense, somebody is telling you that I want this to be done now. I don't want you to reorder things. Okay. Because if you reorder it, probably my semantics of what the storage operations that I am doing are going to be not the same as I want. Okay. Essentially, it's saying I am sending you a command to make sure it is done then and there, don't reorder my request for this thing. Okay. The same thing about here also, all commands received with a simple queue tag message after a command received the ordered queue tag message regardless of initiator executed after that command. Okay. Okay. So, it has to be executed only after I finish this part. Okay. Again, there are issues with respect to if I mix tagged and untagged requests, and it turns out that most of this mixing is usually considered an error. Again, if you just read one of them, IO process received from initiator without a queue tag message, while there are any tagged IO commands in the command queue from that initiator is incorrect initiator connection. Okay. So, basically, if you try to mix tagged and untagged, there are going to be some problems. Okay. So, and there is also a resolution of these errors. They basically says that drive removes all commands in queue from that initiator, aborts the command in progress, okay, and sets the sense key. Sense key means basically it is saying that if the initiator wants to know what happened, that sense key is basically the information that will be sent to the target to the initiator, saying that something bad happened, error condition, I am recording it, you can look at it later. Again, let us just quickly look at Scsi error models. Again, the reason I am going through in some detail is because if you are designing a storage system, whatever level you are working at, you have to really worry about all these kind of situations. Okay. Example, if I look at NFS, I have the same situation. Okay. Let me go through this and I will relate it to the NFS situation. You have some problems called bus reset. Why does it happen? It sometimes turns out in an electrical system, there could be unexpected behavior because of some malfunction of a particular device, and it may turn out that there might be what are called excessive reflections on the bus. Okay. You may want to reset the bus. Okay. So, now there has to be semantics about this resetting. There can be one type called hard and soft. In the hard case, you basically kill all active and outstanding IO processes and reset the state of the target. That means the disk or whatever it is, it can forget about whatever state it has accumulated during the processing so far. Okay. Essentially, you reset it to some previous known good state. Okay. In the case of soft, you are basically saying that you believe something to be a transient error. I want you to try to complete the outstanding IO process, and please do not change any state that I accumulated so far, okay, with respect to the device. Okay. So, again, let us look at NFS. Okay. In NFS also you have something like I connect to a particular remote file system. I can have what is called a hard mount and or a soft remote or a soft mount. Okay. Now, of course, the semantics are slightly different. Okay. In the soft mount case, I try to do it a few number of times, and then if I do not succeed, I stop. In the case of hard mount, I keep on trying it till I get access to it. Okay. Of course, it's not the same as the way the hard and soft the words are used here. I just want to mention that there will be similar issues at any level. Okay. Whatever level, and even the application level also might have similar issues. Okay. So because there are queues also, you may want to say that I need a situation where only one initiator related thing is a problem, okay, or there is some issue with respect to one particular target routine, okay. I want to only kill those things. So a clear queue basically says I want to selectively kill certain things, okay. So there are various types of selective killing, and I think it is best studied by yourself, okay, if you want to look into exactly all this, what these are. Okay. And there is one thing which is called ACA, it's called auto contingent allegiance or something, and basically what it says is that if there is an error, it is basically saying that please don't eliminate that error information right before the next request. Okay. Basically it has to be read. Okay. So there is something important, I don't want anybody to proceed to the next request before it has been read. Okay. So it's some kind of important error information. Okay. So basically if you look at Scsi, it is a client server architecture, and because of this client server architecture, you can see that it has survived for quite some time, and the Scsi protocol also takes into account slowness of devices. Again, whatever protocol you are doing, whatever level, even at application level, you need to worry about what things you are dealing with. Okay. So again, Scsi protocol at the lowest level talks to slow devices like disks and tapes and whatnot. So it actually takes into account the slowness of devices. Okay. So for example, it tries to do some flow control with at the protocol level itself. There is something called ready to transfer commands, so that the target can indicate to the initiator that it's ready, it has buffered the thing, it has got the buffers ready to accept the data. Okay. It also has to take into account parallelism where possible, because these are slow devices. As much parallelism that you can exploit, it's better. Okay. There are errors that also can crop up, and you have to figure out how to handle the errors. Okay. One thing about Scsi is that it doesn't have any security model. Okay. Nowadays, when you have disks with encryption, then this is, as far as I know, is outside the Scsi model. Okay. So again, to repeat one more time, Scsi layer handles many of these issues in its own way. Any other layer above will have to handle similar issues in its own particular ways. Okay. And it's a good protocol if it knows the entities it's dealing with. Okay. So having an accurate model or a reasonably good model about the kind of devices that you're dealing with or entities you're dealing with, that actually has a significant impact on your design. And Scsi has many of those things. So if you're familiar with some of the protocols, Scsi might look a bit strange, precisely because it is handling certain things which are not common with other protocols you might have looked at. Okay. I think I will stop at this point, and we'll continue the next class on I think I'm not clear what I'm going to talk about, but I think I will talk about fiber channel possibly. Okay, thank you.